This is the third mini lecture for section 14.1. Okay, two events are said to be mutually exclusive if their intersection is the empty set. Okay, so in terms of events and probability, what this means is that they can't both happen at once. Okay, so if you have two events that have a Venn diagram, you want to think in terms of Venn diagrams. You have these two events, E and F, and they have a little bit of overlap. Okay, remember that overlap is their intersection. Okay, so these are not mutually exclusive. Okay, on the other hand, you could have a pair of events that don't overlap. Okay, and if they don't overlap, they are mutually exclusive. Okay, in general, if E and F are mutually exclusive, then the probability of their union happening is the sum of the probabilities of each. So when I talk about the union of two sets, remember that means I just put them together into one big set. An outcome is favorable to the union if it's favorable to E or to F. So what this means is that the union of the two sets corresponds to asking the probability of at least one of them happening, or possibly both. So for example, what's the probability of rolling at least a less than 4, or at least an 8 on a single roll of 2 dice? Let's look back at that chart that we had. We can think of this as a Venn diagram. We already had this set here, getting at least an 8. Maybe that's F, we'll say. Then the set corresponding to what we would call E, that's the event in which we got at most 4. No, less than 4. So that means 2 or 3. Less than 4. That set looks like this. Okay, so we could call that set E. So we have these two sets, and you see they're mutually exclusive. You can tell that from the picture. They don't overlap. Okay, so they're mutually exclusive. So the probability of getting less than 4 or at least 8 is equal to the probability of getting less than 4 plus the probability of getting at least 8. And there were 3 ways to get less than 4, so that's 3 out of 36. There were 15 ways to get at least 8, like we just worked out. And I add those together and we get 18 out of 36. Okay, which is 0.5 or 50%. If you want to write it as a decimal or a fraction, or as a percent, that's fine. But often I don't. I often just leave it as a fraction without even reducing it, because it's often helpful to remember the size of the sample space. So 18 out of 36 in some ways might be more useful than 1 over 2, even though it is 1 over 2, and for some other things that 1 over 2 would be better. Okay, so let's try another one. What's the probability of obtaining at least one heads up on a single toss of 2 coins, a penny and a dime? Well, there are several ways of looking at this. We're talking about one heads up on a single toss of 2 coins. So I could just try to write down how many heads up I got. And in that way there would be 3 possibilities. So we could use S equals, I'll say 0, 1, or 2, depending on whether we got 0 heads up, 1 heads up, or 2 heads up. Or what's another way of looking at it? Well, I could write down how each coin lands. The penny could be heads or tails, the dime could be heads or tails. I could draw a little chart here where, okay, I get heads or tails for the penny, and then heads or tails for the dime. And if I look at the outcomes like that, see, I could get heads, 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 tails, tails, heads, and tails, tails. Okay, so there's 2 ways of looking at the sample space. And this is the one I want. Why? Because that's the case in which they're equally likely. Okay, so those are the ones that are equally likely. Okay, well, our event is the event in which we get 1 heads up on a single toss of 2 coins, at least 1 heads up. So that could be heads, 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 tails, or tails, heads. So, if I drop the little Venn diagram here, then it's these 3. It's 3 out of 4. So the probability is 3 out of 4. And if we had answered 2 out of 3, that would have been wrong. So when you toss 2 coins, there's 2 different ways of getting the heads and the tails. So you're more likely to get heads, tails than you are to get tails, tails, for instance. Now, notice that in this problem, we're not able to just add the probabilities. So let me rewrite my Venn diagram here. Heads, 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 tails, tails, heads, tails, tails. So I could think about the event like this. It's the probability of getting the penny heads up or getting the dime heads up. The penny of getting the probability of getting at least 1 heads up is equal to probability of the penny being heads up or the dime heads up. Or, of course, possibly both. Okay, but this is not equal to the sum of those 2. So I'll just say penny heads plus probability of dime heads. Okay, so the reason I'm pointing this out is that, remember in this last example, there we had 2 mutually exclusive events, And the probability that one or the other would happen was just the sum of the two probabilities. In this case, we have events that are not mutually exclusive because they have a common outcome. There's an outcome that's favorable to both. And therefore, the probability that one or the other happens is not equal to the sum of the two probabilities. If I thought it was, then this would be 100%, because this is 50%, this is 50%. If I add them together, I get 100%. But we know it's not 100% probability to get at least one heads up. It's 75% probability. And the reason this would be mistaken is because it double counts what they have in common. So in general, if E and F are two events, maybe mutually exclusive or maybe not, then the probability of E or F is the sum of the probabilities of both E and F minus the probability that they both happen. That's the intersection. Okay, so that would correspond to the heads in our last experiment. Okay, we subtract that because it gets rid of whatever we might have double counted. So for example, what's the probability of getting a 5 on at least one die in a single roll of 2 dice? So I'm going to draw a part of the picture for this. I don't want to try to add it to the Venn diagram that we already had, but we have these two events in which we get at least one 5. So it could be this row or this column. Let me just draw the row and the column so we don't have to reproduce the whole chart. Oops. Sorry. Okay, so within that whole set, 36 outcomes, we have these two events. The one in which the first die gives you a 5, and the one in which the second die gives us a 5. So the probability of getting at least one 5 is the probability of the first giving us 5 or the second giving us 5. So this is equal to the probability that the first will give us 5 plus the probability that the second will give us a 5 minus the probability that they both give us a 5. That's what this intersection is. So we have, 1, 2, 3, 4, 5, 6, 6 out of 36, plus 6 out of 36, minus the overlap, which is 1 out of 36. So we get 11 out of 36. So, in general, you can basically add the probabilities, but you have to subtract the overlap.